All right, so I started recording. So welcome to the lecture. So as far as I was informed by Prof. Coulter, you guys did do exception handling, and then you finished it. So today we'll be starting with a new section. I've already uploaded the lecture slides to Eve, so you can like have a look at them. But so we'll be starting with linked lists, which is a very important concept in computer science. You will also learn more about linked lists in Computer Science 3 when you do advanced data structures. Um, so we will be doing like very basic structures that you can build, or data structures that you can build using linked lists, which are like linked lists themselves, like singly linked lists, doubly linked lists, and circular linked lists. And we will do stacks and queues. And I think that's pretty much how far we're going to get with regards to Computer Science 1B. But in your third year, you'll do more interesting things, like how you can create graphs, like graph data structures using linked lists, and how you can create like tree data structures, um, like different kinds of trees, like binary trees, red-black trees, 3-4 trees, and so forth. And then you get to a point where you do things like skip lists and so forth. And so all of these data structures are important for their particular purposes. You also realize that if you want to get into fields like AI, for example, you need to have a really strong background of data structures. So I hope this is exciting for you guys. It definitely is an interesting topic because linked lists are very powerful. They allow you to use the memory that you can have access to, like with regards to your operating system, in a very creative way. And they are very flexible compared to normal arrays because, like we will actually look at some of the shortcomings that you will face when you use like conventional arrays. Okay, so in this chapter, you will learn about linked lists. You'll learn the basic properties of linked lists. You explore insertion, deletion operations, and deletion operations on linked lists. You'll build and manipulate a linked list, and you will construct what is called a doubly linked list. Okay, so data can be organized and processed sequentially using an array, which is called a sequential list. And the reason an array is called a sequential list, okay, so this is not part of semester test 2. This is not part of the scope for semester test 2. Um, the scope for semester test 2 was actually listed on Eve. So an array is a sequential list in the sense that in memory, an array is stored as contiguous blocks, right? So it's one block after the other. And so to put it simply, it's a sequence of memory addresses that follow each other, right? So the memory addresses are literally next to each other, right? So let's say the first element of an array was at memory address 1. The second element of the array will be on memory address 2. And the third element will be at memory address 3, and so forth, right? So it is like literally sequential, even in terms of how it's stored in memory. So the problems with an array, so one of the problems with an array is that an array is fixed, right? And that limits the things that we can do with an array. Because even if you think about, for example, like a dynamic array, right? In order to increase the size of a dynamic array, you actually have to do a lot of work because you have to destroy the entire array, and then you have to allocate memory for a new array that is bigger than the previous array. And then you have to copy through the elements from the previous array to the new array, right? That is how you create a new array, right? Even if you are using pointers, right? You still have to follow that convention, right? And with the fixed length array, well, once you create a fixed length array, like once, like you can't resize it, So yeah, because it's managed automatically for you. Okay, so those are the problems with arrays, right? So we will find ways in which we can create a list where if we want to add a new element during the execution of a program, we don't have to deallocate memory for the entire list or dynamic array and then reallocate new memory, just to add one element, right? So yeah. Okay, so and then with an unsorted array, searching for an item is slow because so think about it. If you have an array that has values that are not sorted either in ascending order or descending order, you have the problem that uh, like you don't know where the value you're looking for is. And because you don't know where the value you're looking for is, it means that you have to search the entire array until you find that value, right? So if that value is at the end of the array, well, tough luck because you have to literally evaluate each element of that array until you get to the end. And if the value is at the start of the array, well, you were lucky because that's the best case scenario. And when we get to a point where we do computational complexity, which will be towards the end of the semester, you will learn like about best case scenarios and worst case scenarios, like for algorithms and searching and so forth. And then even with a sorted array, insertion and deletion is slow. So searching is faster with a sorted array because then you know exactly where an element is, right? If an array is of size 10 and it has the values 1 to 10, then it means that, value 1 is, at position 0, right? That's easy to find. But then insertion becomes a huge task because in order to keep the array sorted, it means that whenever you insert an element into that array, you will have to move the other elements so that the array remains sorted. So insertion and deletion is slow because it requires data movement. So both of these have their trade-offs. And usually it depends on the task that you're trying to accomplish. If you're building a program where you only have to add elements once in 10 years, then it's better to use a sorted array because you will be searching for the most part. But if you're building an application where you always be inserting and removing elements, but you'll be hardly searching for elements, then it's better to have an unsorted array because then you will be hardly searching for an element. So it depends on the application. Okay, so let's look at linked lists. So the simple definition of a linked list is that it is a collection of items which are usually referred to as nodes containing two components. So a node always has, or usually has two components. The first component is data. So that's the data that is actually stored inside of the node. And then the second component is the address, which is basically a link to the next node in the list, right? So I'm sure you guys can already see how this is advantageous because if I can store an address to the next element of the list, it means that the next element does not have to be, or rather the address of the next element does not have to be next, to me for this to work, right? If I'm at address 1, I can store, like the next elements can be at address 15, as long as I have the link to that element, right? That's the most important thing. So it means that I can have these different nodes in memory, which are not next to each other in terms of memory addresses, but because there are links between these nodes, then I can create a list, even though these nodes are not next to each other. And that's the basic idea behind a linked list. Okay, so let's look at an example, right? So just before we actually even look at this, a linked list usually has two things. It usually has what is referred to as a head and what is referred to as a tail. So in this case, as you can see, we only have a head. Every linked list will have a head, right? Some linked lists don't have tails, like circular linked lists, for example. because the tail will always point to the head. So then they just have a head, right? But so every linked list will have a head, right? And then the head basically is usually a pointer. You can't hear anything. Okay, can the rest of you guys hear me? Okay, well, yeah. So I think, yeah, the students should try and refresh. Let me just type something here. Yeah, all right. Okay, so hopefully they're able to resolve that issue. But yeah, so the head of a linked list will usually have an address to the first element of that list, right? And the head doesn't store any data, right? So as you can see, the head just stores a memory address, right? So the head is just a pointer, basically. A head is a pointer. It's not a node, right? But you'll see, like when we actually implement this in code, we will use a node as a head, because of like of consistency purposes, right? We want to just be able to assign pointers around and stuff like that, right? But the most important thing to know about a head is that it is just a pointer, right? A head is a pointer, and the pointer just stores a memory address, right? It doesn't store any data, right? The pointer doesn't store data, it stores a memory address. So as you can see here, the head is storing a memory address, and that memory address is this memory address here, right? So in this case, the head stores a memory address, and that memory address is this memory address. And when you dereference the head, which is the pointer, you will then get the data that is stored inside of that memory address, right? And then this memory address then is the memory address where the first element of the list is stored, right? So as you can see, we have a 45 at this memory address that is pointed to by the head. And then at this location, right? So remember, so this is a node, right? Which means that it stores data and a memory address, right? So the memory address that is then stored here is a memory address to the second element of the list, right? And then there's also a value and a memory address at that element. And then the value is 65, and then the memory address will point to the next element of the list, and then there's a value there, and then there's a memory address, and then that memory address will point to the next element, and then there's a value and there's a memory address. But then as you can see, this memory address is not a valid memory address, so this is now pointer, right? So it's basically the memory address 0 in a computer, because no program is supposed to have access to that memory address, right? So this is usually now pointer. So the last element of a linked list will always, like its link, right, will always point to now pointer. Okay, so this is just like a more detailed description of what's happening. So as you can see, 1200 is stored in head, which is a memory address. And then when you go to memory address 1200, you will find a value, right? And then because this is a node that is stored in 1200, it means that there's also a memory address that is stored there, right? And then when you go to that memory address, you will find the next node, right? And then the value is 65, and then there will be a memory address there, and so forth. So that's the basic idea behind the linked list. Okay, so why does the tail not wrap around to the head? So the reason, so this is called a singly linked list, right? So this is a singly unordered linked list. As you can see, you have 45, 65, and 34, which means this is not ordered. And then, so in a singly linked list, you want to know when you are at the end of the list, right? But if the, sorry about that, if the tail points back to the head, right, then it becomes a circular list. So you just keep like wrapping around the list, right? So the reason you usually have a head and a tail is so that you can simply ask the question. So think about if you are traversing this list, if you like your, let's say you are outputting these values in the list, right? So let's say you have something like a while loop, right? And then you need to have a guard condition, right? So if you have a guard condition, you could say something like, while like the next address is not now pointer, then keep traversing, right? So that's the whole idea. So then you traverse all the way until you get to this last node. And then when you look at the next address, it will be null pointer. And then you'll be like, oh, okay, well, I'm at the end of the list. So that's the idea behind it. Okay, so I hope that answers your question. Okay, so usually a node is declared as a class or a struct. You'll see in our implementation in the course, we usually declare a node as a struct, right? Because remember, our convention is that if you only have data and you don't have behavior that is associated with the data, then you use a struct, right? But if you want to incorporate behavior, which is member functions, then you use a class. So in our case, because the node will just contain like data, right? Which is the data, and in this case, it will contain a pointer. So then we use a struct. So then the data type of a node depends on the specific application, right? So I think what this actually is supposed to mean is that the data that is stored inside of the node depends on the specific application. Okay, and then so the link component of each node is a pointer. So then the link component, which is the address to the next node, is a pointer, right? So we make that a pointer because we want to store a memory address, right? So then how do we declare a node? We simply declare it as a pointer, right? So the reason we declare nodes as pointers is because we want to create them and destroy them as we wish, right? According to our wishes. We don't want, for example, to create a node and wait. Let's say I create a node inside of a function, and then I have to wait for that function to terminate before I can destroy that node, right? So I want to be able to destroy the nodes whenever I like, and I want to be able to create them whenever I like. So basically, I want to manage their life cycle manually, right? So then it becomes a pointer. And then you'll see why that is useful, right? And also remember, I said a head is a pointer, which means that it needs to store the memory address of the first element of the list, right? So the easiest way to do that is to create, like, make all nodes just pointers. And then when I want to assign a head, when I want to make a head point to the first element of the list, I can just do it by simple assignment, right? I can just say head is first node, right? And then the address stored in first node will simply be transferred to head. So it's much more easier to work with linked lists when you declare the nodes as pointers. Okay, so let's look at some properties of linked lists. So here's a linked list with 4 nodes. So 1, 2, 3, 4. And then, so in this case, we have 17, and then that's the memory address of the next node, memory address of the next node, memory address of the next node. Then you can see memory address 0, which is equivalent to null pointer. And then here we have head. So head, we use head to basically keep track of the start of the list, right? And you also see why that is important. So think about if you're creating a class and you call the class linked list, right? When you add a node, for example, in a function, right? So obviously you create that node at the start of the function, and then when the function terminates, then that pointer will be destroyed, right, automatically. Or rather, you won't have access to that pointer anymore. You won't have a means to access that pointer. So this is like a placeholder, right, that we have in our class. So you store the head, for example, as a private member variable, right? And then it's what you use to access the first elements of the list. And that is what is nice about linked lists, right? You don't have to keep track of the entire list, right? You only need to know where the first element of the list is. And then from the first element, you can access the rest of the elements, right? So that is why it's important to have the head, right? Because it's just a pointer that tells you where the first element of the list is. So it just tells you where the list starts. Okay, so now then what we have here is we have head, and then you can see that the value stored in the pointer is the memory address 2000. And then, so that's that. And then if we then dereference the pointer, and then obviously then we get what's at memory address 2000, and then we can get the member of the struct, which is info, and then the value of info is 17, right? So because head is 2000, and the info of the node at location 2017, right? And then if we say head link, remember, so that means we're dereferencing the pointer, and then we're accessing the member called link. So link obviously is also a pointer, so we are simply getting the value stored in the pointer, which is a memory address, and then that memory address is 2800. And then so if we say head link info, then obviously then we'll get to memory address 2800, and then info is 92, right? So it can get like a bit, intimidating at first, having to keep track of all these pointers and all these links and, all of this, like what's happening here. But like with time, like the more examples we do, the more intuitive it will become. Okay, so we also usually, like when we write code for linked lists, for example, like traversing through a list or replacing nodes in a list, we use a pointer called current, right? Which tells us, which allows us to know where we are in the list. Remember, head is only useful for telling us where the start of the list is. And we can't move head around, right? That's very dangerous because we might forget to move it back, and then we forget where the first element of the list is, and then that results in memory leaks because we have pointers in our program that were not properly deallocated, right? So we usually never move head, right? So head remains head, right? So we don't move this, and then we only move the current pointer. Okay, why is the last address 0? So 0 is memory address 0, right? So a programming, a computer program is not allowed to have access to memory address 0 in a computer, right? So most programming languages use 0 for the null memory location, right? So this is similar to just saying null pointer, basically. Okay, so here, so then we have this current, and then so then what we do is, so at first then we will for example, say current is head, right? And then if we say current is head, then what's going to happen, that's going to copy the memory address stored in head, and then it will be stored in current, which means that current and head will be pointing to the same memory address. And then if we say current info, we'll get the same results as head info. And then if we say current link, we'll get the same results as head link. If we say current link info, we'll get the same results as head link info, right? As we did here in the previous slide. Okay. All right. So, but now we can move current, right? So we can treat current as a cursor, right? We can move current. So then we can say current is current link, right? So then when we do that, remember current link is this pointer here, right? Which stores a memory address. So if I say current is current link, I'm simply copying this memory address and then I'm pasting it in current, which means that current is now pointing to what current link is pointing to, which is this node here, right? So if I keep doing this, let's say this is a loop, for example. If I say while true, and I say current is current link, this is just going to keep going forward. Or if I say while current is not null pointer, current is current link, then current is going to keep moving until current points to memory address 0, and then my loop will terminate, right? So this is how you can traverse a linked list. Okay, so this is just an example again of what will happen. Okay, so let's look at linked list operations. Okay, let me just check for questions. Okay, there's no questions. Okay. Okay, so traversing a linked list. So these are the basic operations of a linked list, right? So you can search for an item in the list, right? So this is if you're looking for, let's say, a 5, then you would just traverse the list until you find the item 5. You can insert an item in the list. So inserting an item is like so it's not like a one-step operation. So we will see how we can insert items in the list, and then you can delete an item from the list, right? But this is usually what you would do uh, with linked lists. Okay, here's a question: how does it not get confused which link it is pointing at? Okay, so okay, so in terms of okay, I don't know what you mean. How does it not get confused? But um, so remember, so here we just like basically we're just storing values and memory addresses in memory locations, right? So whenever you assign a memory address to a pointer, right, then the pointer is storing that memory address, right? So if you want to dereference that memory address at any time, then you can use the arrow operator to dereference the pointer, and then which will also act as a member access operator, which will then give you the value at the memory location, right? So as long as you do like the operations correctly, right, then you shouldn't have problems, right? Linked lists can be tricky. I remember when I was learning linked lists for the first time, I used to get my program used to crash a lot because I used to wind up accessing, like invalid memory locations. Like, I wouldn't insert items properly or delete items properly, and so forth. So, but it takes time, right? So the more you practice, the more you get the idea behind it, and then it becomes more natural. Okay, so traversal. So given a pointer to the first node of the list, step through the nodes of the list. So that's the basic idea, right? So you create a current, and then you make it the same as head, which means that current and head will point to the same memory location, and then you have a loop, and then you just check while current is not null. So while it's not memory address 0, you do the processing that you want to do, and then after doing the processing you want to do, then you move on to the next node, right? Which is just current is current link, right? So that's the basic idea of traversing a list. So here's an example. So you start at the head, so current is head, and then while current is not null, so this is the processing that's happening here. You are just basically outputting what is stored at info, and then you're outputting a space character. So, and then you move to the next node. Okay, so we've already seen this, right? So basically node stores info, and then stores an address to the next node in the form of a pointer. It's also worth mentioning that when we create linked lists, maybe like for example during tutorials, we will mostly be like creating templated lists, right? So usually the int here will be a t, and then you have like template type name, and then all of that stuff, right? So that you can create a list that can store data of any type. Okay, and then variable declaration. So then you have node type. Okay, so this is basically how you create a node, right? So we already spoke about that as well. And then to insert a new node, let's say with info 50. So here's an example of insertion. So here we want to insert this new node with the value 50, right? So we want to store 50 in info, right? And then we want to insert it after P, right? So we want to insert it after this node here, right? So then what we do is So the first thing we do is we create the node, right? So we create the node, and then after creating the node, then we say new node info is 50, right? So we store what we want to store in the node, and then we say this node. So the link from this node, right? So this node's next neighbor, right, will be whoever P's neighbor is, right? So whoever this neighbor is, right? So remember, P is current, right? So it's the current pointer that we spoke about here, right? So it's the same as current. So it's this, right? So they just changed current to P, but it's the same thing. All right, so then we just say, so node link, so which means, actually, I think it's easier if I draw this. Let me actually draw this. Oh yeah, actually here's a schematic here. Yeah, okay. Because this is much better if it's done like, if it's drawn like step by step. Right, but so basically, and then so just to quickly discuss the rest of the code, and then so node link is p link, right? And then now, because I've made node link p-link, then I make p-link new node, right? So what I mean is that I'm just making this point to my new node, right? So my new node will basically be between 65 and 34, right? And then here's a diagram. So here, when I say node is new node type, so this is what happens, right? I'm just creating a new node pointer, right? Remember, this is a pointer. So I'm just creating a new node pointer, and then it doesn't have info yet, and it doesn't have a pointer to the next node yet. And then when I say new node info is 50, I'm just adding 50 to the node. And then when I say new node link is p link, then what I'm doing is I'm saying that this node, the pointer to the next node for new node will basically point to the same location as what this node is currently pointing to, right? So I'm making this node point to what that is pointing to. Right, and then when I'm done, then I say p-link is new node. So I take this old node and then I make it point to this node, right? So and then my list is complete, right? So then everything is nice and great. So that's the basic logic behind it. So insertion, deletion with nodes is faster than arrays, as you only change one node addresses compared to shifting the whole array. Yes, so that's the whole idea. That's perfect. You put it 100%. So it's better than arrays because you only go to the particular memory address that you are looking at, and then when you get there, you simply reconfigure the connections, and then which is usually a two-step process, right? Because all you do is you just make your new node point to whatever that node is pointing to, and then you make that node point to the new node, and then you're done. So so in terms of computational complexity, when we speak about computational or algorithm complexity, my words are really bad this morning, but this is called a constant time operation, right? What that means is that it's not a like a linear time or a polynomial time operation, right? So we will it'll make sense when we get to that point. But for example, shifting all the elements of an array is much more expensive, right, than actually just adding an item to a linked list. Okay, so so let's just see. You can use 2 pointers to simplify the insertion code somewhat. Yeah, so you can also use 2 pointers if you feel that will make it more simpler. So for example, you still have your p pointer that points to this location of the list, and then you have the q pointer that points to the next location of the list. And then so basically what you would do here, you just say new node link is q link, and then you would just say p link is or rather you'd say, sorry, not q link, because q link would be this, right? So you can just say new node link is q, right? Which means it's this memory address, which means that new node would point to that. and then you just say p-link is new node, right? Yeah, but really, so what we usually do in the course is we just use one pointer. We just have one current pointer, and then we prefer to use this operation because it's pretty much the same thing. Okay. So, so this is just inserting using two pointers, as I explained. So when you say p-link is new node, you're just making that point to new node. And then when you say new node link is q, you're just making new node point to whatever q is pointing to. Okay, so in this case, the node with info 34 is to be deleted. Oh yeah, so this is deletion. So if we want to delete the node with info 34, then what we do is we don't go to 34, right? So our pointer, we don't make it point to that the node that we want to delete. We make it point to the node that is like one node before the node we want to delete, right? And then so basically what the reason we want to do that is because we want to first make this node here. We want to point to the neighbor of this node, right? We want to first make this point to the neighbor so that we don't lose this connection to this. We don't lose the memory address of this neighbor, because the only way we can access the memory address of this neighbor is through this neighbor, right? So if we delete this neighbor first, then we won't access this memory address and we will lose this neighbor forever, right? We'll never be able to find it ever again, right? So then we want to first go to the neighbor that is previous to the neighbor to the node we want to delete, and then we want to make that neighbor point to the next neighbor, right? So that is what's happening here. And then after we do that, then we can delete this neighbor here, right? Yeah, so then, for example, in this case, so we'll say p-link. So p-link is p-link link, right? So which means that we want to point to that, and then okay, but then in that case, yeah, this actually is not correct, because in that case, then we would actually lose this memory address. Yeah. So this is actually an example of leaving this as a dangling pointer, right? Because then if we do this, then what's going to happen is then we can't delete this because this is already pointing to that. Yeah, so this is a good example. And then, so as you can see, the node with info 34, this one, is removed from the list, but the memory is still occupied, right? So we have successfully removed the node from the list, in the sense that if we traverse the list from the head, we will not go through the node, right? Obviously, we'll skip through it, but it's still there in memory, right? So it's still a dangling pointer, right? We don't want to do that. So then what we usually do is we assign another like node to it, like another pointer. So for example, we'd use the pointer q, and then so that we can make this point to the next one, and then we can just delete q, right? So then and then after we delete q, then we've made it a point that we've deallocated that memory, and our program no longer has write to that memory address, right? So yeah, so the first step is then to make sure that we make q p-link, right? So remember, so this is p, so p-link is still 34, right? So then q will now point to 34, and then we say p-link is q-link, right? So which basically means that we are doing this operation, but the nice thing now is that we have q, which points to 34, right? So then we can just delete q. So that is how we properly delete. Yeah, so this is a diagram showing that. So basically we have q, so the statement q is p-link, basically just makes q point to p's neighbor, and then And then when we say p-link is q-link, then we are basically saying that we want this to point to whatever this guy's neighbor is, right? So then it points to that, and then we delete q. So then we deallocate 34, and then we don't have a dangling pointer. So yeah, okay. So I think okay. Well, we still have 3 minutes. So let's go to building a linked list. So if data is unsorted, the list will be unsorted, right? So if obviously like if so this is an example of an unsorted list. So as you can see, we have 45, 65, 34, 76. So definitely unsorted. So we can build a linked list forward or backward, right? So when we build a linked list forward, basically a new node is always inserted at the end of the list, right? So that's the basic meaning, right? And then backward means that a new node is always inserted at the beginning of a list, right? This should actually give you an idea, um, because this can actually refer to two different kinds of data structures, right? If you're always adding a node at the end of a list, you can think of that as creating a queue, right? Because in a queue, for example, if you think about a queue data structure or like a queue at a bank, right? Whenever someone joins the list, they always join the end of the queue, right? But then when you when you remove an item from the list, you would remove it from the front, right? And then in terms of building a list backward, that would be similar to a stack, right? Where you always add an item to the top of a list, which is how computer memory works, right? And then, but the difference with a stack is that you add to the top and you remove from the top, right? So yeah. Okay, but a list can be built forward, which just means adding a new node at the end of a list. And then it can be built backward, which just means adding an element at the front of the list, right? So you can think of it as adding to the tail or adding to the head. Okay, so you need 3 pointers to build the list. So you need one to point to the first node in the list, which cannot be moved. So sorry about that. This is the head pointer, right? So remember when I mentioned that you cannot move the head pointer, right? So that's the one pointer you need, right? You need it to point to the first node in the list, and then you cannot move it. And then you also need a pointer to point to the last node in the list, and that is usually referred to the tail of the list. And you usually cannot move that pointer as well, right? So you only make these pointers. Oh no, wait. So this is building a linked list forward, yeah. So then in this case, you would only move the tail of the list, but then the head you cannot move it. So you always add an item at the end of the list, and then you need another pointer to create the new node, right? Which you will add to the list. And then so an example where you have data, which is 2, 15, 18, 24, 34. So then here's an example. So you'd have your head and your tail. And then your head will point to 2. Your tail will point to 2. And then new node will also point to this memory location, which is 2. And then when you have a new node, which is 15, so then head does not move. It's always pointing to 2, but now last will move and it will point to the new node. And then the new node pointer will point to the new node, right? And then you make the 2 point to the new node, right? And so forth, right? So the process repeats itself until you are done adding your elements. So I'm going to stop here. And then so Prof. Kulto will continue from building a linked list backward. But yeah, so I hope this does make sense, at least theoretically, like logically outside of code, because that's the most important part, right? It has to make sense logically, right? Before you even start writing code. And then when you start doing tutorials, then it should make sense programmatically. But I will stop here and thank you very much for your time and do enjoy the rest of your Friday. Thank you.